Welcome to this lecture series in real analysis. In this lecture, we'll discuss the very important concept of absolute convergence of a series, and let us recall some relevant things. So we've previously discussed what is a positive term series. Despite the name, it is only a series whose terms are non-negative. We do not insist that each term in the sequence is positive, only that each term is non-negative. So a series of this sort is called a positive term series if each an is non-negative. Okay, and we saw that if you have a positive term series, then the sum of the series can be expressed by taking the supremum of all the partial sums, or taking the supremum of all the partial sums along finite subsets. And this value may turn out to be infinite, and that's okay. When it turns out to be infinite, we do not say that the series converges, but still it is meaningful to say that the sum is infinite in an obvious intuitive way. All right, then we have this natural notion of rearrangement of a series. If we have a series, then a rearrangement of it is any series of this form, or rather I'll write it like this, where sigma is a bijection, from n to n. So we are rearranging the ordering in which the terms appear, and that's why the name, rearrangement. So this is a formal object, this is another formal object, and we saw that if a series converges, it is possible to find, it is possible that a rearrangement of it may not converge. Right? We saw an example where I think the example was something like that. I think this is what we saw. Anyway, there exist examples. You can construct many by yourself. And however, we have one result regarding this misbehavior, or against this misbehavior, which is if you have a positive term series, then this pathology doesn't occur. If you have a positive term series, then any rearrangement of it converges to the same sum. So this is a succinct way to express that. All right. So what did I say? If you have a positive term series which converges, then any rearrangement of it converges to the same sum. And if your original sum was infinite, which is when the series did not converge, the rearranged sum will also be infinite. And the linchpin of this fact was basically the simple observation. Anyway, this is not very difficult, but in today's lecture we'll generalize this, and we will see that if you have an absolutely convergent series, whatever that means, we will define. If you have an absolutely convergent series, then it is also stable under rearrangements. It does not change the nature of convergence or divergence under rearrangement. If you have an absolutely convergent series, then it converges, we will show that. And that even if you rearrange it, it still converges to the same sum. So a positive term series will be a special, or a convergent positive term series will be a special kind of absolutely convergent series. So this is a true generalization in that sense. Okay. Here is one problem for practice. It's a very nice problem, and I think we'll use it at one point in this lecture. So let me mark it with a star. Okay. So what is the definition of absolute convergence? A series is said to be absolutely convergent if the following series is convergent. So a series is absolutely convergent if the corresponding series of absolute values is convergent, and hence the name. So the name is not mysterious. And note that this is a positive term series. So to any series, you can naturally associate a positive term series, and we have a definition. Note that every absolutely convergent series is convergent. Right? One way to see it is using Cauchy's criterion. So what you do is you sum up to, the main problem is notation. You sum up to 1 to m, or rather you sum from m plus 1 up to n. Right? We want to say that this can be made arbitrarily small, provided m and n are large enough. So whenever this happens for some sufficiently large n, we want to show that this is smaller than or than epsilon. So that's Cauchy's criterion. I'm not being too detailed here. So this, just notice, is less than equal to by triangle inequality. Yeah, now it's fine. By triangle inequality we have this, but this can be made arbitrarily small by the assumption that the series is absolutely convergent. You can make this arbitrarily small if m is chosen large enough. I mean, m and n are chosen large enough, only then this sum makes sense. So that's it. That's the argument. I'll put a ... because I don't want to write it down. So that's the reason why every absolutely convergent series converges. So it is a stronger notion of convergence, clearly. And to see that it is strictly stronger, here we have a series which is convergent because of the problem that I showed or I posed in the beginning. So this is a special case of the problem set. There we had a more general situation, but this is a convergent series. However, it is not absolutely convergent because what is the corresponding positive term series? The corresponding positive term series is nothing but the harmonic series, meaning this one, which we have shown is a divergent series. So we have an absolutely convergent series. Sorry, we have a non-absolutely convergent series, but it is a convergent series. So there exist convergent series which are not absolutely convergent. I may have jumbled up during my enunciation, but let me say that again. This series is convergent, but not absolutely convergent. It is convergent because of the thing given in the problem set. It is not absolutely convergent because the corresponding positive term series is the harmonic series. So the notion of absolute convergence is a strictly stronger notion than that of convergence. It is asking for more. Okay. This is also easy to see. This is immediate from triangle inequality, right? So if you just sum up to the nth, or rather, what I want to say is, what is clear is the following. So fix any large capital N. Then by triangle inequality, we have this. And now, since this sums up to something finite, this limit also exists and is finite, right? We are assuming absolute convergence. So the limit of this as capital N tends to infinity is finite. And so is this. And since this inequality will be maintained for each capital N, it will also be maintained in the limit, and which is what this means, right? Since the series is absolutely convergent, this is meaningful because absolutely convergent series are also convergent series. So when I write this, I meant the number, or rather the sum of the original series, and this is the sum of the corresponding positive term series, and this is this inequality is there because of triangle inequality at the nth level. Anyway, very, very simple things. And now, before we prove our main result, which is that absolute convergence is stable under rearrangements, whatever that means, we will write a precise statement, but to get there, we will talk a little bit about permutations, very little. So first we have a notation, which I don't know if we'll use too much, but for any natural number, we write this to mean that set. It's convenient. Do not confuse this with the greatest integer function or anything. That would be silly because the greatest integer function of n is n. So that's not what we mean. And anyway, I make the floor function like this and not like that, even though some textbooks use this notation. So anyway, the notation that we have is when we write bracket n, we mean the first n natural numbers. Now, here is a simple lemma. Fix any bijection from the naturals to the naturals. In other words, fix a permutation of the naturals and fix any positive integer capital N. Then there is some positive integer p. I do not mean a prime, just a positive integer p, such that the first capital N natural numbers are contained here. Now what is that? This is same as that. This is the image of the first p natural numbers under sigma. So that is same as this set. So this containment is same as, just a different way of writing the following more traditional way of writing. This is a trivial lemma, but let me still try to justify, and writing down a formal proof will not help. Let's just understand this by taking small values of capital N. Suppose capital N was equal to 1. Is this true? Well, if capital N is 1, just find some, since sigma is a bijection, there is some p such that sigma p is equal to 1. Right? Since sigma is a bijection, 1 has to be in the image of sigma. So just find a p such that this happens, and then clearly this holds. Right? So that's that for n equals 1. What about n equals 2? Well, there is some p1 such that this happens, and p2 such that this happens. Again, because sigma is a bijection. And now you can check that this set of the first two natural numbers is contained here. There's nothing to check. This is equal to that. These two sets are equal. But this is clearly contained in sigma of the first p natural numbers, where what is p? P is max of the two, the bigger of the two. That's it. So that proves for n equals 2, and the same kind of reasoning you can do for any capital N. So it's a trivial lemma. Still, it will help to have isolated this separately. Okay, let's move on. Yeah, and I think this is our main theorem. Fix any absolutely convergent series. Then, first, every rearrangement of it is also absolutely convergent, and further has the same sum. Right? So, yeah, so let's try to prove this. I encourage you to pause the video and try to prove this yourself. It is not at all a hard thing. Okay. So, if you followed the treatment or the lecture on positive term series, the fact that every rearrangement of it is absolutely convergent is trivial, right? Because what are we saying? First, we are given that this is finite. By absolute convergence, we know this is finite. And if you fix any permutation of the naturals, you get this rearranged thing. And since this is a positive term series, and this is a rearrangement of that series, this is also finite. In fact, it is the same as the previous sum. So any rearranged series or any rearrangement of the original series is also absolutely convergent. That is not the difficult part. In fact, there is no difficult part, but this part is trivial. We now want to show that this is the case. Where sigma is some arbitrary fixed bijection or arbitrary fixed permutation of n. So want to show this fixed. Let me erase this because it will clutter things. So fix a bijection want to show that this happens where we already know that this is a genuine real number and that is a genuine real number because this converges and that converges, because this is an absolutely convergent series, and by the same reason this is also an absolutely convergent series as we just argued. So we would just want to show that the sums are the same. Okay, and for the sake of just notational convenience, I will write this thing as, or maybe I'll write it separately here. By a sigma n, we will abbreviate that as bn, just an abbreviation. All right, so we want to say that these two sums are the same. What does that mean if we consider the sequence of partial sums? So let Sn denote the sum of the first n terms of the first series and Tn denote the sum of the first n terms of the second, of the rearranged series, right? So fix epsilon greater than 0. Want to show that, or I will write suffices to show that. Suffices to show that there is some positive integer p such that this is less than epsilon whenever n is at least p, right? So just make sure you follow this. What do we want to do? We want to show that the limit of this, which we know exists as n goes to infinity, is same as the limit of this as n goes to infinity. And if we show this, that the nth numbers in this sequence of partial sums, they are coming closer and closer, that shows that they will have the same limit. So I hope you follow this blue thing, that if we just establish this part, then we will be done. Okay, so now by Cauchy's criterion, we know that there is some natural number n such that for all n at least little m at least capital N, we have this is less than epsilon by 2, I will write. That's immediate from Cauchy's criterion because the series was absolutely convergent, right? This is a convergent series, therefore by Cauchy's criterion we have that. Okay. And now let P be such that the first capital N natural numbers are contained in the image of the first P natural numbers. So this is the previous lemma. Such a P exists by the previous lemma. Okay. So now for n at least P, we have Sn, or rather I'll write Tn minus Sn. This is equal to summation, right? Just unpacking the definitions, which is another unpacking. That thing. But note that if I write down the list of the indices that I see, sigma 1, sigma 2, up to sigma little n, I am sure to see the numbers in some order, 1 up to capital N. Because little n is at least p, and this containment is there, we also have this containment, right? Because little n is at least p, so we have that containment. And therefore, in this list, I'm sure to see the numbers A1 up to A capital N in here. And similarly, I'm sure to see the same. I mean, here it's absolutely trivial. And yeah, here I can say that where we may assume. In fact, I'll write it here. So let P be at least capital N. In fact, it has to be. So yeah, perhaps it's better to note that. Here I just want to make a note that P is at least capital N. Why is that? Because of this containment. Here there are capital N things. If there were less than capital N things here, this containment couldn't have happened. So we have that. And therefore here, when I look at the terms here, I am also sure to see A1 up to AN appearing. And therefore those capital N terms will cancel out. So after I cancel them out, this is same as I am going to sum up. I'm going to sum up over which indices, just so that I do not have to deal with the first capital N thing. So this I will explain a little bit, but it's best understood by yourself. And here I do not want to see the faces of the first N things. What did I do? I just cancelled out these terms from here and here. All of them appear here and all of them appear there. So I just cancelled them out. And what is this notation? This is the pre-image of the set of first capital and natural numbers under sigma. Maybe I'll put a bracket to make it even more clear. So this notation just means that, right? And this thing is contained there, right? Because what did we have? We had this is contained in there, but since N is greater than P, we have this containment, and all I've done is just taken the pre-image. So it's all meaningful. This thing is contained there. So we have just knocked off all of the indices corresponding to this set in here, and we have knocked off some of the indices here so that the corresponding terms cancel out. So just make sure you follow this. And therefore, now if we are on the same page here, then we see that if N is at least P, then this difference is that difference, which is at most by triangle inequality. That much. But what about this? This is less than equal to K at least capital N plus 1, and the same thing for the other guy. So try to understand this. Instead of little n here, it would be better to write one more step. So what I'm saying is that this thing is less than equal to, I'm just writing a bigger set. Right? The set of indices, I have just expanded that. So this inequality is not a problem because everything here is a non-negative real number. And this, or rather this sum, is exactly equal to that sum. Because what are the things that you won't see? What are the indices that you won't see if you vary over this indexing set? Precisely the first capital and natural numbers. So it's equal. I mean, here I could also write an equal to sign, but anyway. But what about this? By Cauchy, this is at most epsilon by 2. And the same for the other one. Because just look at this thing. How did we choose capital N? We chose capital N so that this is true. Whenever M and N are chosen to be at least capital N. So I can take N going to infinity. and here I would have n plus 1, and therefore this less than equal to will just become this less than sign will become a less than equal to sign, that's all. So that's what I'm using here, and therefore this is equal to epsilon. Epsilon. So what have we shown? We have shown that this is at most epsilon for large enough n. So let me just amend this a little bit. Doesn't change the mathematics, but just to be a little bit more coherent. So yeah, so that's the proof. I hope you followed. And again, it's just best to write down this proof on your own, as it's true for every proof. These technical details of the proof may have thrown you off, but if you think about it by yourself, it will be extremely clear. It's not at all a hard thing. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.